this button here, and then that button, this other button. Okay, ready to go. How's everybody doing? All right, welcome to the few and the proud who still come to lecture this far into the semester. Nice to see your smiling faces or your foreheads while you look at your phones. It's all good. Let's see, in terms of announcements and things, you had another homework go out, so that's cool. You've got a final exam coming out, Friday quizzes, and that's basically it for the rest of the semester. We have a pretty straightforward cadence for this course. So I think, let's see, is this homework 4, 3, 4? Oh, okay, so you're almost there. Cool. Any questions, comments, concerns? I think at this point, if you haven't figured out the cadence of this course, you're probably in some trouble. I'm not gonna lie. Excellent. Okay, and many thanks to those of you who keep me company in my office hours, and for those of you who don't, your grades are actually measurably lower. I checked because the people that are in my office hours were basically just doing the homework together. So that's on you. Right, so today we're going to continue in our discussion of optimization. You might notice that, like, relative to some lectures in this course, I don't have to rely on my notes quite so much for these ones because this happens to be aligned with like what I do in my day job, which strangely at MIT is probably research and not teaching. But essentially, we're continuing our discussion of optimization here, which really is at the core of this course. I mean, even when we talked about numerical linear algebra, we tried to do so in really an optimization-oriented lens, where we talked about least squares problems and so on. In our previous couple lectures, we went from all the way, like numerical linear algebra in some sense is a very specific case of optimization, and then we zoomed pretty far into the general side and talked about really generic algorithms for minimizing some function f of x, right? So for example, we talked about a gradient descent algorithm and actually proved a condition under which it converges with a constant step size, which is kind of nice. And now, and then after that, we talked about, well, what can we do to make it go even faster? And in particular, in our previous lecture, we derived techniques called quasi-Newton algorithms. In particular, one of these things, which basically kept a history of your gradients and function values to build up an approximation of the Hessian. Anybody remember the algorithm we derived? 6 of you just like whispered it, I heard at the same time, and yet nobody raised their hand. It's early in the morning. Yes. BFGS. All right, for fun bar trivia, anybody remember the 4 names attached to BFGS? No, me neither. Okay, but those are, of course, academics who should receive lots of credit for their hard work and interesting algorithm, which really is the standard in a lot of corners of optimization. By the way, even in machine learning, if you turn on the BFGS option in PyTorch, it usually does okay. I think it's relatively competitive with the things that people like to use. Okay, so all of those algorithms are for convex and non-convex optimization, but they all did not allow us to have a constraint, right? So far, we've just been trying to minimize a function f of x, but we've not said like subject to something else. And of course, in a lot of corners of engineering and computer science, we need constraints in our optimization problems. Now, we actually have seen one example of a constrained optimization class problem so far in this class. Namely, we looked at problems of the form minimize the norm of ax squared subject to the constraint that x has norm 1. And just for a little bit of review, do we remember what is the, what comes out of this problem? Yes. Me here, you got this. How do I solve this problem? I know you know. That's right. This is an eigenvalue problem. Thank you. It's good to strike fear in the hearts of our students at the beginning of lecture. Okay. That's absolutely right. So we have considered one optimization problem with constraints, and so far our strategy for doing this has been kind of uninteresting. Like we just kind of work out the optimality condition, namely using Lagrange multipliers, everybody's favorite piece of machinery, set it equal to 0, kind of see what happens, and reduce it to some other numerical problem we know how to solve, right? So in this case, in particular, if we add a Lagrange multiplier lambda on the constraint, probably after squaring, then this leads us to A transpose AX equals lambda x. Yeah. And you guys are all good at that because you had to practice it on your midterm, which someday will great. Okay, but today we are going to consider a different problem, which is even more generic and takes the following form, which is minimizing a function f of x subject to 2 constraints, g of x equals 0 and h of x greater than or equal to 0. And here g and h are vector valued functions. meaning that they input a vector x and they output a vector of constraints. So they can be more than one of them at a time. Right? This is the world's most generic version of constraint optimization. Because so far we haven't put any assumptions on f, g, and h. Now in reality, we're going to think of these as nice differentiable functions that we can work with. One thing that you should note is that this is extremely generic language. Do you see that? In fact, it kind of encapsulates almost every problem that we've studied so far in this course. So for example, let's say that I wanted to do root finding, which in the timeline of this course was now ancient history. Does anybody have any suggestions? If I have a piece of software that can basically take pointers to functions f, g, and h and output a minimum of this problem, could I implement root finding? I see a nod. Jonah, help me out. How could I do that?
Well, I think you see it right. The root finding problem is like f of x star equals x star, right?
That's fixed point, but close. F of x star equals 0.
Equals 0.
Yeah.
So we're going to minimize x, like argument x, and g of x equals 0, and then we don't care about the greater than or equal to.
That's right. So, or maybe to translate Jonah's answer a bit, I could solve the following, which is minimize 0 subject to g of x equals 0. And notice that in order to solve this problem, I have to find, at the very least, something called a feasible point. Meaning that, like, in order to say that I solved even this problem, I need to at least find an x that satisfies g of x equals 0, and then I've minimized the objective. Yeah? Or similarly, if we do equality constraint optimization, that's just dropping h. Unconstrained optimization is just dropping g and h, and so on, right? So this problem form essentially encapsulates a huge number of computational problems, right? So let's think for a second. So we have a mystery attendee in our course today, our postdoc Sina. Everybody say hello to Sina. There's Sina. So let's say Sina, as the brilliant MIT postdoc that he is, comes in and sells you, he comes to your company and he says, look, I've got this amazing piece of software. All you have to do is give me pointers to functions f, g, and h and their derivatives, and I will give you, you run my code and it gives me an x star, which minimizes the problem on the screen. Should we trust Sina? How many of us vote yes? One person does, and they're right, because Sina is a fantastic postdoc. How many of us vote no? How many of us are like, I refuse to raise my hand. This is an uncomfortable question. There's a human being involved. Yeah, there are a few hands. Right, so the answer is no, right? Because this is a really hard problem. Basically, you can take almost any problem in all of computer science and write it in this form for a carefully chosen f, g, and h. By the way, this includes discrete problems, right? So for example, let's say that I add a constraint that xi is equal to, or xi squared is equal to 1. So I just take one of the elements of xi and I add this. This is a differentiable constraint. You see that? Now, what did I really do? Like, this constraint is equivalent to saying that xi is in the following set. So I can actually take a lot of non-differentiable problems in computer science, like binary things, and start adding constraints that look like this, which feel algebraic and kind of nice. Those fit into this form perfectly fine, and now I can study problems that are actually binary in nature. Do you see that? So this, essentially, this is all to say that, like, this problem form is extremely generic. Algorithms that solve this, you don't expect to do particularly well unless you know a little bit more about f, g, and h. Yes?
Out of curiosity, like, what sorts of problems can't be cast in this form?
What sorts of problems cannot be cast in this form? That's a good question. I would say it depends whether you want the, like, smart-ass mathematician answer or the real answer. I mean, like, you can do a lot of weird things to cast problems in this form. So for example, a thing that you see in theoretical proofs in computer science, which you should never do in reality, is say, like, I don't know, let G be the indicator of the convex hull of the set of all programs written in binary C++ that halt. That's a convex shape. This is actually a continuous constraint, but it's not an object that you actually have access to. So there are a lot of problems that you can write in this form that you wouldn't. I would say in reality, when we restrict ourselves even to just differentiable f, g, and h, you have to be careful because this includes a lot of NP hard things. So it's actually not so hard, for example, to write traveling salesman problem in this language. All that said, a lot of times we say, I don't care. I would like to find some local optimum of this problem. F, G, and H have gradients, and I just want to find something feasible that does better than before. And actually in a lot of applications that's perfectly fine. So for example, in corners of engineering, I might not expect to like build the world's best possible bridge between point A and point B, but at the very least I expect to do better than like a randomly generated thing that I used to start with, right? And so the algorithms in this domain are perfectly fine from engineering perspective, right? In the very least, they can often find local optima, but this is all just a warning to say that like expecting these things to do super well is rather optimistic. Incidentally, in this course, we're going to assume all these functions are differentiable as many times as we want. There's a whole other universe for non-differentiable optimization, which is even more generic. The textbook actually includes a little bit of discussion of this. Interestingly, when I sent this to the publisher and went through their editing process for the first edition, they had two pieces of feedback. One was any worthwhile textbook must discuss non-differentiable optimization, which was surprising to me because I don't think anybody, like relatively few people use these tools unless they really know what they're doing. Right, this includes like these kind of spiritual things like genetic optimization and ant colonies and all these other, they tend to be like connected to nature systems, which I think is largely a reflection of how hard these problems are. You start resorting to like things around you that look like they might work. And then the other thing they made me do is go through the textbook, and every time it said such that, I had to change it to subject to. I don't know why, but apparently that was the other piece of feedback. In any event, hopefully what I've convinced you is that these problems are pretty hard. I mean, simultaneously in this notation, we've encapsulated root finding, minimizing things that are unconstrained, finding feasible points of a set of inequalities. All of these things fit into this notation. Okay, now, because this is such a generic problem, it is really not hard to find applications of this machinery. The textbook contains a few. One of the simple ones is as follows. So actually a very typical 3D modeling tool out there. It used to be called blobbies. These days they have neural implicits and so on. Have functions whose zero level set is some surface. So for example, maybe I define g of x to be equal to the distance, maybe signed, meaning that it's like negative on the inside and positive on the outside, to the surface. And then notice that if I want to solve like a projection problem, like I'm given some point and I want to find its closest point on the surface, I might write something like this. This used to be a thing that graphics people called blobbies, where they would write these g of x's as like a sum of Gaussian functions, and you could use it as a little 3D modeling tool. These days, I think we've mostly replaced these with neural networks, but it's exactly the same thing. So a neural network will like predict the distance to some surface sitting in 3 space. If you wanted to actually find the closest point to some location in 3D, you have to solve a problem like this, where now this guy is like a neural network, which is pretty crazy. So the textbook actually contains an image of what this looks like, if you're curious. It's an extremely non-convex and ugly problem. Now notice this is the case where the objective function is pretty nice. It's just a bunch of circles, but then the constraint is the thing that makes this problem really nasty. Another one that comes up a lot. So we've talked in this class about least squares quite a bit. At this point, you must be sick and tired of least squares. Tina's nodding, but he's been to like 2 lectures of this course. He doesn't even have to do the homework. I'm picking on our postdoc today. So let's say that I'm doing least squares, but I have an additional piece of information, which is I know that there's a positive correlation between my features and the thing I'm trying to predict, right? So like, I don't know, I'm trying to predict the height of a plant, and I know that as I add more water, at least for small amounts of water, as I add more water, the plant gets taller, and I want to add that as a constraint. Then one thing I might do is minimize ax minus b, but now add a constraint like x being positive, right? So now I can't have a negative correlation. Sadly, every single algorithm that we've talked about in this class no longer applies because we've added this constraint. This particular problem is a relatively nice one because it's convex with a convex constraint. Come back to that later. But still, we need some new algorithms for solving this thing. And in fact, the algorithms we'll cover today and probably in our next lecture are more or less the things that people use in practice to solve things here. In manufacturing, sometimes there's other problems. So for example, these problems are actually very close to my heart. So my PhD was in an area of math called optimal transport, which is all about matching supply to demand. So like for whatever reason, it's very popular in France. So I usually talk about like I've got a bunch of bakeries that are distributed about a map of Paris and a bunch of like flour refineries? Like things that make flour, and they're located in different locations. I know the distance between every flour source and every bakery, and each one makes a different amount of flour per day, and every bakery has a different demand, and I'm trying to route supply to demand that minimizes cost, like these kinds of problems. So now I have a constraint, like every bakery needs the amount of flour it needs to survive for the day, and I'm trying to minimize like the, for example, I mean, maybe the product of distance traveled by flour times the amount that I carry. As an economist, I think you could debate whether that's really the right objective function, but that's typically the mathematical model. And that leads you to problems that kind of look like this. Or here's a different one, which is like maybe maximize profits, right? So maybe xj is the amount of every product that I manufacture, and pj is the amount of profit I make per product, right? So I probably want to maximize that, unless I'm in academia. I have to make a positive amount of every product, right? That's the first constraint. But at the same time, maybe I have some limit on the supply of all the different ingredients that go into that product, which gives me a different constraint on this problem, right? Anybody know, like this problem has a particularly nice structure in that the objective and the constraints are all linear functions of x. Does anybody know what kind of problem this is called? I'm guessing many of you encountered it before. Yeah, Alice. A linear program. Notice the linear program are a fantastic example of a problem where you need constraints, right? Because what's going to happen if I try to minimize a linear objective function? Well, its minimum is either negative infinity or it's 0, right? Because flat things don't really have minima. They just keep going down. Incidentally, there's a really cool algorithm I have to mention here and that we're not going to cover in this class because there's only so many lectures, called Frank-Wolf. Which does a really wild thing. So when we talked about Newton's method a while ago, remember, what does Newton's method do? It kind of takes a Taylor series, like a second order Taylor series, to approximate your objective and minimizes it in every step. A reasonable question that I usually get in this course, but I didn't this year because you guys are smart, is like, well, why didn't I just take a first order Taylor series? And the answer is because like linear things don't have minima. Like you need at least 2 terms in your Taylor series for Newton's method to make sense. The exception of that is actually this Frank-Wolf algorithm, which only takes 1 term in the Taylor series, but it makes an additional assumption, which is that your constraint set looks something like what you see here. So in other words, like when you linearize your objective, now it's like this giant downhill direction. You just keep rolling downhill, but at the very least, you know that there's walls around you. And so the Frank-Wolf algorithm does a really cool thing, which is you have your constraint set, usually a polytope, but it doesn't have to be. And then in gradient, like it just computes the gradient, and it just like bangs into the wall in every step, and then just moves a little bit in that direction. This is like one of these crazy algorithms that I've never intuitively managed to convince myself like why this thing should work, but it's actually very popular in machine learning because you only need one term for your problem. So anyway, if you're looking for an advanced topic, it's a thing you can look up. This is called Frank-Wolf. Notice this Wolf guy seems to show up a lot in these algorithms. The textbook actually also covers another problem we'll skip in lecture today called bundle adjustment, where you like take a bunch of photos of a 3D thing from different angles, and now you're trying to like align all of their camera motions. My colleague Vincent Sisman in the ECS department tells me that in 2 years this will all become irrelevant because AI will do it all for us. So I guess I'll skip it today. Also because we're running behind in lectures. the really reality here. This is a really nasty problem, by the way, because you have unknown camera projections that go from 3D to the plane of every image. Those are like the P's. And oftentimes you have like weird constraints on the P's, like the camera projections aren't too wild. You have relationships between them, like if I project into one image, if I move that into 3D and then project into the other, those have to be consistent. So these problems get out of control real fast. In any event, I'm rushing because I think the reality is, and hopefully this is a reasonable assumption, you guys have all probably encountered or can think of a constraint optimization problem somewhere in your everyday life, whether it's economics, computation, machine learning, whatever. Constraint optimization is everywhere. And so it's good to cover some numerical algorithms for this task because once you have them, you know, your possibilities, at least of solving like a huge array of numerical tasks kind of poorly is quite wide, right? So that's what we'll be doing today. Now, a few things to get started. We should have some language we can all agree on. when we talk about these problems, notice, by the way, so let's see, I should write our optimization problem on the board because I'm noticing zipping through these slides. We have minimize over x, f of x, subject to, not such that, g of x equals 0, h of x greater than or equal to 0, like that. Now, one thing that's probably easy enough to convince yourself, like we had 2 entire lectures on root finding, right? So notice that even if I just drop the objective altogether and I say, just find me a point that satisfies the constraints of the problem, that's already, I see your hand, that's already a hard problem, right? And so the set of x's that satisfy these 2 things is called the feasible set. And the usual schematic that we draw is we kind of like draw some little region in space, which is like the set of x's that satisfy the constraint, like this. And then f of x gives like little level sets that are sitting inside of this thing, right? And so our goal is to make f as small as possible, but we have to sit inside of this region, right? So oftentimes, by the way, these algorithms will take place in 2 phases. The first one is to find a feasible point, and then you can do some version of gradient descent that kind of keeps you in the feasible set, right? Like that feels kind of reasonable. All right, question. Oh, that's a good question. Yeah, so this like funny notation h of x greater than or equal to 0 is going to be element-wise. Yeah, we're not going to talk about code programming today, so all that semi-definite stuff we mentioned before is not relevant. Yeah, there is a version where you have that kind of constraint, which I love, and someday we'll teach in an advanced course. Okay. So anyways, the feasible set is a set of points satisfying the constraint, but we don't care about the objective. And our goal today is going to be to try to characterize critical points of this problem, which is essentially a point that satisfies the constraints and also is a local min-max or saddle point. We're going to dive into that in a little more detail. Okay? Now, as a bit of a hint, like, so for example, I drew you a picture here, right? So here, hopefully, I'm sorry I don't have colored chalk, but hopefully you remember what's going on. I've got feasible set, level sets of f. Where's our optimal point? It's like right in the center of this little target here. Now, here's like kind of a funny observation. Notice that this x is strictly in the interior of our feasible set, right? Now, here's kind of a thing that I want you guys to think about for a second. What would the optimum of this problem be if I dropped the constraint? The same thing. Do you see that? Because like the minimum of f, even if I ignored this blob altogether, is still going to be that center point, right? This is going to be a case that we call inactive for obvious reasons, meaning that like essentially we're strictly in the interior of our domain. And so actually if we had dropped our constraints, the optimum wouldn't have changed. To draw a contrasting situation, suppose my level sets of f looked like this. Now my optimum is probably going to be like here-ish. And notice if I dropped the constraint, in this case, my optimum would move, right? Because essentially it kind of it's like it yearns to leave the feasible set, right? This is called an active constraint. And essentially we're going to spend our entire lecture today trying to kind of characterize the difference between these 2 things, okay? All right. So suppose we didn't have an h, we didn't have an inequality. What's been our strategy for solving the equality constraint case so far in this course? Just borrowed from calculus? Lagrange multipliers, that's right. So essentially, a really convenient thing happens for us in the equality constraint case, which, notice that, like, essentially we're taking calculus and we're kind of just building layers of abstraction around it, right? So like in high school calculus, like when you wanted to solve optimization problems, probably for the first time, you thought about that. You took derivatives, set them equal to 0, and that was pretty cool. And then in multivariable calculus, you said, oh, but now I've got an equality constraint, so I can't take derivatives and set them equal to 0 anymore. So now I've got to do this souped up version called Lagrange multiplier. Sadly for us, I just made our problem a little bit more general. I introduced this third thing. So now Lagrange multiplier doesn't work anymore. And the natural question is, can I still do some version of Lagrange multiplier that's even fancier than this one, right? And our hint, I'm going to keep giving intuition because I feel like the derivation ends up getting a little yucky kind of numeric, symbolically. But notice the picture that we drew here. We kind of have two cases, right? Here, right, when my optimum ended up in the interior of the feasible set, I could have just dropped the constraint and nothing would have changed, right? So in some sense, if I knew the list of inactive constraints, I could just remove them from my problem. That'd be perfectly fine. But there's a chicken and egg issue there because I don't actually know what they are. On the other hand, here, notice what happened. I added my inequality constraint. And where did I end up? Did I end up just in any old place in the feasible set? No, I ended up specifically on its boundary. So do you see what happens? This is actually a point where h is strictly equal to 0. So notice like kind of an interesting thing happens. There's like a really crappy version, like a 2 to the n version of Lagrange multipliers we could do here, right? Where I take all of my inequality constraints and I convert them to equality constraint, solve this problem, and then find the one that was optimal for the original one, right? And that's actually perfectly fine because of this argument, right? Like I just need to know which constraints are active and inactive, and then I either remove them or convert them to equality constraints. That's kind of yucky, doesn't scale terribly well in the size of our problem. So today we're going to try and answer whether we can come up with a better one. Sound good? Now, as usual, because I didn't prepare for lecture, I was baking a birthday cake at 2 in the morning yesterday. I forgot that actually there's a nice picture of exactly the thing I drew on the board that's in our slides. But essentially, again, these are our two cases, active and inactive constraints. Notice, by the way, that we have to do this for each h, like each element of h one by one, right? It could be that like the first inequality constraint is active and the second one is inactive. Any questions about our schematic so far? Think now, because we're about to write a bunch of symbols. Yeah. It's a good question. I think like for today's lecture, it's actually not going to matter a whole lot. What'll happen is just that the conditions we'll derive will be unsatisfiable if we get a bad point. So the question was like, why, what assumptions we need on the feasible set? Typically, we at least assume that there exists a feasible point. And that's going to be all we need for today. Later in our proof of the Lagrange multiplier kind of analog, we are going to add a different one, which is that our constraints aren't redundant. So in particular, if we have two inequality constraints where we could have just had one, that's going to cause a problem for our proof. It doesn't cause a problem for the conditions we're going to derive, but it does cause a problem for my lazy proof. Yes?
Could you please explain what you mean when you say like the inactive constraint is the case for h of x is greater than 0?
Sure. So the basic idea is that, so if x star is the solution of our problem, then, okay, by definition, h of x star is either strictly greater than 0 or equal to 0. Those are just two cases. We label the first case inactive and the second one active. And the way to think about it is if you are inactive, you could have removed that constraint and your optimum wouldn't change. Yeah, locally. By the way, like we're not making convexity assumptions so far, so this is all locally, meaning that like it could be you remove the constraint and like 1,000 miles away, like something got better. But like here we're just talking about like a neighborhood around x star. Okay, any other questions? Let's go. You might notice in this class I try really hard to draw pictures of these things because I think it's so easy to get lost in symbols, especially in the typical numerical analysis course. Okay, so here are two cases. And again, think about it like whether the optimum has to move in response to adding the constraint or not. Yeah, okay. So here's the idea that we're going to try and make actionable mathematically, as it were. We're going to say, okay, if we remove all the inactive constraints and make the active constraints equality constraints, then we can use Lagrange multipliers again. That makes sense? So like if there was some oracle out there that said like, oh, actually you didn't really need to enforce that like you're not going to use too many eggs in your birthday cake, then you could just drop that constraint. Then like, if you could do that for each of the constraints ahead of time, you didn't really need inequality constraints. You could have just had equality constraint, right? And so what we're going to do is basically just a sneaky mathematical trick to do this without having to know which constraints are active or inactive a priori. I would definitely classify this as sneaky mathematical trick rather than like something super foundational. Like some things, are like really deep. Some things are just like, oh, the notation seems really cool. Like we're going to see a thing called Karush-Kuhn-Tucker condition, KKT. which is like souped up Lagrange multiplier, and they look abstract and weird. And then you realize it's like kind of a weird version of programming where they like took this expression and they just converted it into math. Okay? So that's our goal for today, is to convince you that KKT conditions are really not so complicated. Which is good, because I feel like it's often the thing where students check out in optimization class. So bear with me today, and if you have questions, your goal is to stop me, and we're going to do it together. We'll see if you manage to detect the one sleight of hand in my proof. I think I isolated it, and then I got it wrong. I noticed it's slightly wrong in the book, so I fixed it this morning and printed it out. So we'll see. Only slightly wrong. Okay. So here's going to be a weird thing we're going to do. Suppose all of our constraints were active. By the way, we're going to have like a lot of hypothetical sentences, so I'm going to try and use subjunctive properly today. So like, suppose that we're like not so worried about this whole like inequality business. We could define Lagrangian for our entire problem. I mean, we can define anything we want. We just have to be careful about our optimality condition. So in particular, I'm going to choose to define the following function. Which is the following. So here, I'm going to have lambda of x. We're going to have a Lagrange multiplier for our equality constraint, and another Lagrange multiplier for our inequality constraint. Alicia's like, heck no. And she's right. Like, I shouldn't do this. But I can define anything I want. I just have to be careful how I use it. Yeah? Incidentally, by the way, in a lot of treatments of this stuff, they don't have a lambda at all. They just talk about inequality constraints. Does anybody have an idea why? Notice I could have done the following. If I do g of x greater than or equal to 0 and g of x less than or equal to 0, then those two things together are an equality constraint. The book just does the slightly uglier one, because in my mind, like, this is the worst idea numerically, and anything that even suggests you should do that is not good. Right, because here, if you perturb x at all, which happens because of numerical error, then like you'll just think your problem is unsatisfiable. By the way, where this can come up is like you have constraints that make like some weird singular thing like that. To the question earlier about what assumptions we have to put on our functions, this is the kind of case where like you really, like if you're in real analysis and you care about this kind of stuff, you have to be kind of careful. Okay, so we're going to continue to make Alicia uncomfortable, and the way we're going to do that is by defining the Lagrangian as if all of our constraints were active, even though we know that they're not, right? So in particular, we have f of x minus lambda dot product. I keep forgetting which one's the equality. The g is the equality constraint, and now we're just going to add more Lagrange multipliers. We're just going to go hog wild, as it were, like that. By the way, we're going to do something in today's lecture which I try to avoid in most of this class, which is that we're going to like look at elements of G and H, so we're going to have some indices. The reason, like, you can do this with Jacobian matrices, but I just found myself getting like transposes flipped backward all the time, and if I do, then I'm guessing our students will too. So we're just going to do a few indices instead. Okay, so continuing to make our students uncomfortable, here's the thing that we could do is say like, well, in an ideal world where like all of our H's were active, then I could have written an optimality condition, which is the following. I'm going to put a question mark over the equal sign, because it's not actually true, right? Which says the following. Oh, well, if all of our constraints were active, then I could have had the following condition. Lambda I grad gi of x minus, by the way, I'm going to use i's to index equality constraints and j's to index inequality constraints. And I look forward to the first person who raises their hand when I get it wrong. Mu j hj of x. Now, this is a incorrect statement, right? Because this, essentially, I need to remove terms from this expression that correspond to inactive constraints. Yes, Mihir. Yes, it is gradient. See, that was fast. He gets the prize. Any other mistakes? Cool. So this is like what we'd like to be true because we know how to deal with this stuff, but it's not. So here's a kind of fun observation. Yeah, I classify this as like fun math, which is as follows. I would like to zero out terms when h is not equal to 0. So here's a way that I can actually do this. I'm going to say that the following condition I actually can enforce, which is I'm going to have an and like that mu j times hj of x is equal to 0. Now, this looks like abstract math, but it's actually just programming. Like, if I have two numbers and I say I'm going to force their product to be 0, what is that in words? One of them equals 0. Yeah? So let's think through all the cases here. Suppose suppose that x star is in, by the way, there's like an x star that is in the book indicating that I'm the optimal point. I'm going to drop all the stars because I don't feel like writing it 1,000 times. Let's say that I'm in the interior of the feasible set. In other words, hj, like constraint j, is inactive, right? Then what do we know about hj? It is strictly positive, right? That's the definition of being in the interior of the feasible set. So let's say that I enforce this constraint. Well, if hj is strictly positive, what do we know? Louder for the back of the room, Jonah. Mu j is equal to 0. That's right. Well, if mu j is equal to 0, then I removed that term from the optimality condition. Isn't that sneaky? Let's say that my constraint is active, then hj is 0, and then this thing does nothing. And there's no constraint on mu. Isn't that cool? So this is basically just a sneaky way of removing inactive constraints from the Lagrange multiplier condition. Now you might be saying, like, but Justin, somehow you like wrote Lagrange multipliers and just added stuff to it, and that feels somehow uncomfortable because like somehow inequality constraints should be weaker than equality constraints, and yet I've added something to this problem. Here's what I've removed. Typically, we enforce that like gi of x is equal to 0, right? And like you have to satisfy both of these to be a local optimum. But I'm not going to add that hj is equal to 0. I'm just going to add a weaker condition, which is hj of x is greater than or equal to 0. Okay? So that's how to square that. Does that make sense? So like essentially, we already have 2 of the 3 KKT conditions, which is namely, it's actually okay to enforce that we're at a critical point of the Lagrangian so long as we add this condition, which just zeroes out terms when you have an inactive constraint. Cool? Yes, Alice. Every single j. That's right. Yeah. So I should really have like a. Yeah. Thank you. Yeah, that is, and that's important to note. Like, I think actually a very typical math mistake I see is that they take the dot product between the mu vector and all of the h's and make that equal to 0. That is insufficient. You have to do it for every single element one at a time. So I'm glad you asked that. Very typical mistake. Other questions? Now, what we've shown so far is that these conditions are necessary for being at a local optimum. The question is, are they sufficient? Right? Remember those fancy math words. Like necessary means that like if I'm at a local optimum, these 2 things are true. That much I think we can now agree on. Now the question is, if I check these 2 conditions, do I think I'm at a local optimum? Jonah says no. Why? Vibes, because it's 11:43 and there's still, yeah. That's okay. At least you spoke up. That's more than you can say for the other 20 people. Yes. Yeah, so we clearly need these 2 conditions, right? So by the way, this is called primal feasibility. The word primal we're going to kind of come back to. Yeah. And this is like local optimality. Or there's another term for this, I'm forgetting. It's on the slide, sorry. What was that? Stationarity, yeah. Which is a fancy way of saying local optimal. This thing is called complementary slackness, which I think is a really cute phrase. Complementary slackness is like when my grad students chair an office. And essentially what it says is that only one of these 2 things can be slack at a time, right? Like either this can be greater than 0 or that one, but like you can't have a case where they're both greater than or equal. So there's like slackness is complementary. Only have one at a time. Okay? As like a little bit of a clue, let's say that I flip this inequality the other way. Is anything in the conditions I've written down like like in the calculus part of my problem, actually kind of distinguish between those two? Not really, right? And so it kind of feels like something's missing. And in fact, something is. So let me see if I can draw a picture of it. This is the part where I get extremely uncomfortable trying to draw these things because it's like the angles really matter and that's hard to draw. So we'll see if we can do it. Ugh. By the way, any questions so far about complementary slackness, primal feasibility, or the third one that I forgot again, stationarity? Cool. And we're all convinced so far that these are not abstract conditions. They're actually very much reasonable. That's my goal for today. KKT is reasonable. That's the message I want you to get. Okay. So we have one more condition, which essentially is going to help us distinguish between like the positive constraint and the negative constraint, like kind of differentially. And here's the picture to have in mind. So the thing that we're going to kind of worry about is when I'm at like a corner of the feasible set like this. So here, maybe I have, maybe this is a set of points where h1 of x is equal to 0. Here's a set of points where h2 of x is equal to 0, like that. Okay? We look confused. How can I help you out? No, we're good. Okay. And this is going to be our feasible set. So we're like somewhere in the inside of this thing, right? Yes?
Question, when you were drawing like a boundary earlier,
Uh-huh.
you drew it without any corners, then here you have a corner. Are these like just...
Corners are perfectly fine in this universe. Yeah, you're right. So the picture I drew before didn't have a corner, but if you have two constraints, most likely they'll meet at some angle,
And
right?
is this like the situation where this third constraint matters, or does this constraint need to exist in the corner?
That's a good question. I think it actually matters in both, but it's harder to derive in this case. Yeah. Now, first of all, let's say that this is our feasible set. FS for feasible set. What direction is the gradient of h1 and h2? This is the kind of thing that your instructor likes to get wrong. So remember that the feasible set is a set where the h's are positive. Remember that the gradient is the direction that increases our function, despite the phrase gradient descent. Remember, gradient descent goes along minus the gradient. So I claim this is grad h2, right? It points to the inside of the feasible set, right? And similarly, this is grad h1. And by the way, they meet at 90-degree angles because that's what gradients do. With me so far? So let's say that I'm at a corner, meaning that I have more than one constraint that's active at a time. Okay? Remember, my goal is to minimize f. This is going to be where our picture gets a little bit confusing. Now, let's say that gradient of f pointed this way. I should put some question marks here. Now, because of the way I phrased this sentence, I guess you can probably guess where I'm going with this. Is this a local optimum? Kind of feels like it is. I got an arrow pointing into a corner. That feels optimal coded. Trying to speak Gen Z. Is this optimal? So remember, my goal is to make f as small as possible. Now, what is the world's dumbest optimization algorithm for getting constraints all together? Like we covered it in this class, like or in machine learning. You guys all like you're 2025 grad students, so like you do this stuff every day for your whole careers. Almost all of you do. It's gradient descent, yeah? Now, let's say that I forgot my constraints because I was a forgetful old professor and I took one step of gradient descent. Where would I end up? I would go this way. So I repeat my question. Is this a local optimum of my problem? No, somebody help me out. Oh my God, you're killing me. Anything, give me an explanation. Why is this not the local optimum? Yes.
A little spitballing here.
Yeah.
If we can take a gradient step in the right direction
Yeah.
away from it and continue to satisfy our goal conditions, then it's not.
Yeah, I'm with you, except the wolf part. But you're absolutely right that like, essentially, I just argued to you, I can take a small step of along my gradient, minus the gradient. Remember that decreases f, so it makes my objective function better. And in this picture, I moved to the interior of my feasible set, and that's kosher, that's allowed. So this can't possibly be an optimum. Do you see that? So this is the kind of case that we need to rule out, that the picture above, like the math we've derived so far, just doesn't handle. Does that make sense? Yes.
Why doesn't that map handle this case?
Oh, well, why does it?
It's a great question.
Yeah, no, I mean, like I said, it's just not, like, we didn't use that to argue these equations. It's just not there. Yeah, that's right. Okay. So right. So this is the case that we have to worry about, where like our constraints, like this point, notice that had these constraints been active, this would have been like a reasonable optimum, but there's actually direction we can move that deactivates a constraint and in the process makes the objective better. Now this picture is a little bit, like makes it obvious. I'm going to try and draw one that, oh God. I hate these pictures so much. Let's say that they met at kind of an oblique angle, like that. And moreover, let's say that the gradient of f is, let's see. So I always get these pictures backward. I'm so sorry. We're gonna just draw one and then we're gonna see what happens. Okay, let's say that. So here's my point, and let's say that the gradient of f wants me to go in an infeasible direction. So like somewhere like that. Ah, that'll do it. Okay. Now, you can see me like sweating. As we get farther along, this proof is only gonna get worse. Okay. So from this picture, it kind of feels like, oh, well, wait a second. Like now, step of gradient descent takes me out of my feasible set, so like that argument I made doesn't apply. Yeah? Is this a feasible point? Assuming this is the side that's feasible. Or sorry, is this a local optimum? Interesting. It's about 50-50. Good, I stumped you guys. Now, here's the thing to remember. At least to first order, like, do I have to take a gradient step to decrease f? The answer is no, right? Like, there's actually an entire half plane of directions that I can move that decrease the value of f, right? And what is that half plane? Well, if I draw a vector orthogonal to grad f, roughly that, you can tell it's orthogonal because I drew that little 90-degree sign, yeah? Then any direction that I move in this upper half plane decreases the value of f. Like, I don't have to take a gradient step. I could take a step in any direction I want. I just want to take a step in any direction that decreases f, right? So anything that has a positive dot product with grad f increases f. Anything with a negative dot product with grad f decreases f, yeah? So here's a weird thing that I could do, and this is the case that makes this proof really ugly, and why the proof in my first edition of my book is completely wrong, is the following. Let's say that okay, so here's minus grad f, that leaves the feasible set. So like that I can't do. See, gets a frowny face. However, let's say that I slide along this edge. So I move along a direction delta, right? So I'm no longer doing gradient descent, but I'm just vibing and moving around in the notice I'm moving around the feasible set, yeah? The dot product between delta and grad f is negative. Do you see that? Because it's like more than 90 degrees away from each other. So if I perturb from this point a little bit in the delta direction, what happens to the value of f? Remember that. So let's call this point x star. F of x to first order is equal to f x star plus grad f x star times x minus x star, like that, right? So this thing is kind of like delta plus other stuff, right? So here, this dot product is negative. So what happens to the value of f? Let's take a vote. Does it increase or decrease? How many of us vote increase? How many of us vote decrease? How many of us sit behind the median student in this classroom so they just won't raise their hand? Like, I mean, physically. Huh. Fascinating. So yeah, so this quantity is less than 0. meaning that I could scoot along this edge a little bit and the value of f decreased. So is this point a local optimum? No. Yeah. So notice the situation is a little complicated. Like when I'm at a corner, I have to consider every constraint one by one and make sure that if I can slide kind of orthogonally in the other direction from the constraint, like here, I moved away from this one being active, but I stayed in the active set of the other guy. For every one of those pairs, I got to make sure that f doesn't decrease. Yeah, in higher dimensions, there's even more pairs. Does that make sense? Like the kind of situation we have to avoid. I'm arguing this carefully because I think it's actually quite tricky to get it right. Okay. So that's what we're after, is one more condition. And the kind of funny thing is in the textbook, because it's like math writing, it's like a paragraph to do away with this last condition. But I think actually thinking it through is quite tricky. And this is probably, by the way, like if you look at the history of KKT conditions, they go back to like the 1950s or something. Like they're fairly recent. Like Lagrange multiplier is from a long time ago. Like it's a totally reasonable question. I'm sure some mathematician back in the day asked what happens with an inequality, but like it wasn't really addressed until like pretty recent in math history. Partially that has to do with the history of optimization. Like people went back and reconsidered algorithm. Okay, so far we have these conditions. We haven't distinguished between these cases. And so essentially, here's kind of a fun fact if you think about it. This is again another sufficient or necessary but not sufficient condition, is if I think about the direction that decreases f, that's minus grad f, right? And the direction that decreases h, which means I move in the feasible set, that's minus h, grad h. So if this dot product is positive, that's kind of a good thing, right? Because it means that in order to decrease f, I must leave the feasible set. Whew. This condition is annoying to check because there's a product of stuff, so we don't want to include this. And so the question is, can we do like a cleaner version of this guy? The answer is yes, because obviously, because I'm telling you. Okay. So let's work through our logic a bit. I'm moving too slowly today. We're not going to finish. That's not good. Okay. I'm responding too much to you guys' sleepy faces. I'm falling behind. Okay. So let's say that I'm at a critical point of my constraint problem. Now we're going to call this x star. And what I'm going to do is I'm going to perturb x star to some new point y, which I'm going to call x star plus delta. Okay? And essentially, all of this picture that we've been drawing, right, if we're actually at a critical point, I think you can translate this to, for any delta, one of two things has to happen. Possibly both, but at least one. One is that y is infeasible, meaning I perturbed and I just left the feasible set, in which case it doesn't kind of matter what happens to the value of f. Or y is feasible, but f of y is bigger, right? So this is like sort of the condition that I'm trying to translate into math. And again, that's my point. When we talk about these KKT conditions, each one of them is just translating stuff we can write in words into symbols. That's all. Okay. So in our process of converting to symbols, here's where things get a little ugly. Then we're going to do one little analytical argument and we're done. Okay? So let's think locally here, and let's look at the gradient of hj and take its dot product with delta, and suppose that it is greater than 0. What does that mean? Well, that means that delta moves. I'm writing this out in words because I want us to kind of have a reference as we derive the equations, into the feasible set. Everybody agree with me? I think we said this in a lot of different forms now. Okay. Similarly, if I take gradient of f and I dot product with delta and I get greater than 0, this means that delta increases f. And notice that this is going to kind of help us with these two conditions here. Okay? All right. So here's what we want. All vectors moving into feasible set. In other words, I stay feasible. All of these vectors increase f. That, in words, is the condition that we're missing from our optimality condition. Does that make sense? Yes.
What's the symbol you wrote on
2.
Amplify
This thing. Greater than or equal to.
That's to say when you perturb x by delta, you've increased f.
That's right. I scoot a little bit. The delta, by the way, I'm thinking of as small here. I scoot a little in the delta direction, and f got bigger. Right? Like essentially, one of these two things should always be true if I scoot a little bit. Either I left the feasible set or the value got bigger. Yeah.
That x referring to x stars is its own x.
Oh yeah, x star. Sorry, I keep dropping the stars. That's my bad. Yeah, and then I wrote one, and then okay. Other questions? This is great. You guys are thinking critically. I think it's so easy to check out in a lecture on KKT condition. Okay. Oh no, I lost my mic. Gotta stop wiggling around. Yes, sorry. We don't want to increase f. We want that if we are at a critical point, any perturbation either increases f, meaning it becomes suboptimal, or it leaves a feasible set. Yeah. Okay. Good, good, good. Never wearing this shirt again when I'm teaching. Okay. So all that's left is to translate this to math, and we're done for the day. That's it, really. And what we're going to find is that, like, I'm going to erase this picture. Hope that's okay. We're going to find that this condition is shockingly simple, which is cool, I think. Okay. But the argument is a little finicky. Again, if you look in the first edition of the book or lectures from 2+ years ago, it's completely wrong. Somebody pointed this out, and that's my bad. Okay. So here's what we're going to do. Suppose HK is active. Then we're going to define a particular vector delta, and then we're going to apply these two facts to delta. Okay? So here's what we're going to do. We're going to define kind of a weird object. And this is where there is going to be one mathematical sleight of hand, which is a condition we're not going to check, but I will point out when it happens. Or, Sina will let us all know. Okay, delta K is this object we're going to define. And in particular, we're going to say that this is the gradient of HK, right? So this is the direction we can move around to modify our level set function at x. And essentially, remember that picture I drew that I just managed to erase where, like, I need to worry about sliding along each of those edges that's kind of adjacent? Here's the way that I'm going to do it. I'm going to subtract off the projection of this vector onto the span of a lot of stuff. And this is where I switched to the printout from the revised textbook as of an hour ago, which is the following. The span of, it's actually the union of a bunch of stuff. The gradient of GI, I think in our notation, for all of the I, I forget what letter we use for the G's, but essentially we're going to project out any direction that leaves the G's alone. Okay, and we're going to project out the following. This is the yucky part of our argument. The gradient of Hj, where j is not equal to k, okay, and Hj of x equals to 0. Okay, so let's think about our picture. What is this? This is all of the set of active constraints other than the current one that we're thinking about, right? Oh, and this is the projection of grad HK. Nice. So here's the idea. We have a direction which is modifying the value of our level set function. And here's the sneaky thing that I've done. I've projected out all directions that would affect whether or not any of the other constraints is affected, right? So in other words, like essentially, if the Hj is active, for all the other j's, it stays active perturbatively. And if it's not, then it doesn't. That's what this is saying in math. It's an ugly expression. Okay? So here is what I claim, which is kind of fun, which is the following. By construction, we have the following, which is mu k times the dot product between delta k and grad h j of x is equal to 0 for all j not equal to k. Why is that? Well, notice that this dot product between delta and the gradient of hj for all the j not equal to k, which is exactly what I projected out. Yeah? Or the constraint is inactive, in which case this thing is 0 anyway. Okay? This is what the book that you guys have in your PDF is slightly wrong. It misses that mu factor. And for that, I apologize. Okay. All right. Moreover, we can actually say a second thing, which is what is the dot product between delta k and grad hk at x? Well, remember that if you think about it, right, so what did we do? We took hk, which is some vector, and we subtracted out its projection onto some plane, right? So if you think about it, this has got to be greater than or equal to 0. There's never a case when I project something out and I somehow end up like flipped 180 degrees from where I started. It might be 0, in which case I projected out the whole vector, but it's never negative. Cool? That's the uncomfortable part. All right. So if we put all of this together, well, remember what we want. We need that if we have any delta that stays feasible, which is kind of what we've argued here, right? Then it better increase the value of f, right? So in particular, what we need is that grad f evaluated at our x star, or x Jonah, dot product with delta k. We need this thing to be greater than or equal to 0. Okay. So now, here's where there's a slight mathematical sleight of hand, and I'm going to let you think about it at home a tiny bit because I'm low on time. So far, I've argued that this is greater than or equal to 0, assuming that our constraints are not redundant, meaning that we don't have two constraints that form parallel planes like that. We can say actually a slightly stronger thing, that this is positive. Okay, this is the one thing I'm not going to argue in lecture because I'm low on time, but I'm going to let you think about it. Essentially, under kind of a non-redundancy condition, you can convince yourself that essentially when you project out everybody else, there's still some direction I can move that is interesting and moves into the feasible set. Okay? All right. So that's the one sleight of hand. And for that, I apologize. Okay. So now our proof is basically done, I claim. So here's what we're going to do. Now, we have, is it okay if I erase this expression? Okay. Oh, this is sad. I wanted to cover linear program duality, and I don't think we're going to get to it, but that's okay. Actually, maybe we can squeeze it in. There's a really quick way to do it. Okay. Right, so remember that we have 0 is equal to the gradient with respect to x of our Lagrange multiplier, like that, which is grad f. Oh, yeah. Sorry. Minus the sum lambda I, gi, grad gi. These are all evaluated at x minus the sum mu j, grad hj. X like that. And I'm going to take the dot product of both sides with this delta k. Okay? Now, well, we're going to do that, by the way. We have grad f is equal to the sum of these two things. Yeah? So in particular, we have grad f at x dot product with delta k is equal to, here's the kind of cool thing. Basically, what we just argued is that there's only one term in this whole giant sum that's left, right? And that is mu k times grad hk at x dot product delta k. Right? Do you see that? Like this projection basically zeroed out every other term in both of these two sums. Isn't that kind of cool? I think this is so cool. This is great. So clever. Okay. Moreover, this guy, we argued, had better be greater than or equal to 0. Right? That's there. Yeah. And this one, we argued is strictly greater than 0. Right? That was our non-redundancy condition. What can we conclude? Yeah, I can divide both sides by this dot product, right? And so I get mu is equal to this guy divided by that guy. In particular, these are both positive numbers. So I conclude mu k is greater than or equal to 0. Ta-da! So here's the cool thing. We had all of this logic basically saying that, like, if I move in any direction that leaves all the constraints alone and then moves strictly into the feasible set of one of them at a time, that is equivalent to just asking that your dual Lagrange multipliers are greater than or equal to 0. And that is the final condition of KKT conditions. That's called dual feasibility. It turns out that these are not only necessary, but they're also sufficient, meaning that to be locally optimal for a differentiable problem in calculus with an inequality constraint, there exist Lagrange multipliers lambda and mu that satisfy all of these things here: stationarity, primal feasibility, complementary slackness, and dual feasibility. And the thing I want you to take home is that the first three are actually very simple. Like, we covered those in like 5 minutes. And it's the last one that requires a little bit of argumentation and some kind of careful analysis. But at the end of the day, all it's saying is just that, like, if I'm at a corner, I don't want to be in the condition where I can move in a bit and increase the function. That's it. Cool? Yes, Alice. Why is it called dual feasibility? Oh, I'm so glad you asked. We got time. Okay. Let's think about an entirely different way to solve this problem. I did this without looking at my notes, so they're like 4 pages behind now. That's fun. Okay. Why is it called dual feasibility? Now, the objects mu and lambda that we have defined in this problem have many different interpretations. And in lots of different areas of math, it's kind of one of these ideas that's very natural. So, like, that's why, like, KKT condition has 3 different names attached. It wasn't like 3 people like sitting in a room that came up with this. It was just 3 academics with big egos that all proposed this in different places. Okay, to be fair, I've never met any of these 3 people. I'm sure they're lovely. But because of that, one of the places where this appears quite a bit is in the world of economics. Now, in the world of economics, the Lagrange multipliers have a different name. They're called shadow prices. And that is because the way you can interpret this is the amount of money that you pay to enforce a constraint. And moreover, from that community, the proof that you get of the KKT conditions look very different. So in particular, here's a fun thing that I can do. Let's look at our Lagrange multiplier expression again. So this is f of x minus lambda dot product g of x minus mu dot product h of x, like that. And here is another way to interpret all of these variables here, which is the following. So far, this isn't the right problem to solve, but let's say that I do the following. This is kind of a problem that's borrowed from game theory, which is the following. I can do I'm going to look at the min over x of the max of lambda in r to the whatever. I forget the name of the dimension. This is where I want to double check. Yeah. And mu greater than or equal to 0. So here's how to read this problem. I'm now writing a new optimization problem over x, which is in some sense unconstrained. The objective value for x, like, I put in an x, I want to know how good it is, actually comes from another optimization problem where I maximize the inside over unconstrained lambda and positive mu's. Now, I claim this is equivalent to our original problem. Let's see why. So suppose that x is infeasible. Like, suppose g of x is equal to 17, right? Or 73, either one works. Okay? Then what is going to be the solution of the maximum here? So x is infeasible, and now I evaluate this thing as a function of x, which is itself an optimization problem. It's a little abstract, yeah? Usually in game theory, you talk about it like I play an x and you play a mu and a lambda. So if I want to play a mu and a lambda that makes this thing as big as possible, what should I do? Well, notice there's a product between lambda and g. right? So if x is infeasible for g, meaning that g of x is not equal to 0, the solution to the inner problem is infinity. Do you see that? Because I can just put a giant lambda in front of g of x, or a very negative lambda, depending on the sign. So from perspective of this game player, the guy that's trying to choose x, if this guy's goal is to make the inner function as small as possible, they'd better choose an x that's feasible with respect to g. Yeah? Similarly, let's say that x is infeasible with respect to h, meaning that h of x is negative. Yeah? Well, now notice what happens. Well, if h of x is negative, I can choose a positive mu that blows up this other term because there's a minus in front of it. Yeah? So notice that this kind of unconstrained problem we call this extended real numbers, meaning that the function of x here can also take the value infinity. This problem as a sort of unconstrained one is actually constrained because like the outer guy, it's in his best interest to choose a feasible x because otherwise your objective of the inner problem is infinity and that's not so good. Does that make sense? So this is a sort of game theoretical interpretation of Lagrange multipliers. Essentially, there's actually two optimization problems happening. The primal, which is this guy, and the dual, which is this guy. Yeah? And in fact, one question you can ask in more advanced math courses is, let's say that we change perspective, and we now think about the guy that's playing the maximization problem. So probably his problem looks something like the following. Maybe you maximize over lambda and mu greater than or equal to 0, and then you minimize over x, the same Lagrangian. The question you might ask is, when are these two problems equivalent? Right? In other words, like when do you reach a kind of Nash equilibrium kind of thing of this problem? There turns out to be exactly the KKT conditions, right? That essentially half of the conditions here are optimality for the first player, the other half are optimality for the second player. And notice that, by the way, in this version of the story, the fact that mu is positive actually just comes right out of the definition. We don't need all that arguing. What you need instead is to make sure that you're sort of stationary with respect to both problems. Now, I think this is such a cool interpretation of this problem. It's kind of fun to think about. It also gives you a shortcut. So those of you who have taken operations research style course, you probably spent about 6 weeks computing like duals of linear programs. When we say duals, that essentially means like, what is the optimization problem in lambda and mu that corresponds to the problem in x? Here's the thing I learned after grad school is that exercise is totally useless. Here's a very fast shortcut for how you can do it that I consider to be way more efficient than what they cover in those courses. So let's say I have a generic linear program just for fun, which looks something like the following. So here, let's say I have minimize b dot product with x subject to a x is greater than or equal to c. A very generic problem. So I'm given a matrix A, a vector C, and a vector B. This is my optimization problem. Right? This covers, like, for example, that supply and demand problem we wrote before. All right, so what is our primal in the language there? So it's going to be min over x, and we now got a max. Notice there's no equality constraint, so we just have a mu greater than or equal to 0, like that. And we're going to have b dot product x, I always get the sign backward, minus mu dot product ax minus c, like that. Everybody agree this is our Lagrangian? By the way, this is also a totally reasonable way to derive KKT conditions just by hand on an exam or something. It's pretty efficient. Okay. And it's a good way to remember the sign of this guy. It's whatever one blows up the constraint. Okay. These are all typical mistakes. So the dual to this problem just swaps the min and the max. Yeah? So in particular, here's what the other game player is doing. They maximize with respect to positive mu the min over x, it's supposed to be an x, b dot product x minus mu dot product a x minus c, like that. Now, so far this doesn't feel particularly exciting, but let's actually rearrange this expression ever so slightly. This thing is equal to, if I rearrange, I've got an x dot product b and an x dot product a transpose mu, right? So I can write this as x transpose B minus A transpose mu, like that, plus mu transpose C. Does everybody agree with me that these two things are the same? I'm rushing a little because I think this trick is cool. I don't want to share it. Okay. So let's think about the outer guy's problem, right? So his job in life is to maximize this entire bracketed expression, which itself is solving a minimization problem with respect to mu, yeah? Now, similarly, let's say that he chooses a mu, so that this quantity is non-zero. Then what is the inner game player going to do to make that minimization as bad as possible for the outside guy? Well, they're just going to choose an x that makes this thing really, really, really negative, right? Like minus infinity, which you can do because you just blow this thing up, right? This is just a dot product. Everybody with me? So clearly, from the outside guy's perspective, should it ever choose a mu for which this is not zero? No. Yeah? So the outer problem can be written in a slightly different fashion, which is to say, well, basically, kind of implicitly for that problem, there's a constraint, which is the following. So now we have maximize over mu. We've got a constraint that mu is greater than or equal to 0. This came from before. Yeah? And essentially, this guy should never choose something that gets minus infinity for the inner min problem. So in particular, he or she should choose one where A transpose mu is equal to B, right? Because otherwise that inner problem is going to blow up. Now the contribution of this term to the objective is 0. And what's left is mu dot product with C. And this is what we call the dual of the linear program. So in fact, all those like weird conditions that I feel like people check in classes like this, where they give you a bunch of formulas and then you're like taking transposes of matrices and so on, I think it's completely unnecessary. This is a much easier way to write it. You write the minimax version of your problem, you swap the two variables, and then you just reparenthesize. Like that's why I never remember those formulas. And this is what you get. So essentially, the difference between KKT conditions and this is only whether or not you can swap those two problems to get the same thing. It turns out you can always do that locally, but globally sometimes you can't. And we'll leave that for a more advanced course. But if the inner problem is convex, that typically is pretty close to what you need. If you want to read a little bit about the advanced version of the story here, by the way, this is all kind of a preview into advanced math. The main thing I want you to get is KKT condition. There's something called the Slater condition, which is a sufficient condition for being able to swap the min and the max in this problem. And it's very easy to check. Essentially, it just says, if there exists a point that is strictly in the interior of your constraints, then you can do this kind of thing. Yes?
Were you saying you can only swap the min and max at when the KKT conditions hold, or even?
I guess that's right in some sense. It's sort of a circular thing because they're sort of equivalent to one another. But yeah, I guess that's right. It's simple. I think the way I would think about it is like this is an alternative way to get to the KKT conditions from a kind of game theoretical perspective. The reason we went with the other proof is that we did not derive a condition under which you can swap the min and the max, and that is a tricky thing. So this is more just like a pointer into advanced math and a very efficient way to do this in practice. Do you see that? Like essentially, like it's easy to get the sign of the dual feasibility condition backward and that kind of stuff. But from perspective of this minimax problem, it's pretty clear which way it has to go. Now, the last stuff that we have to talk about, which of course we don't have a lot of time for, I see the clock, you guys don't all need to turn around, is essentially algorithms for solving these problems in practice. But the takeaway is that actually they're very easy. Once you have these conditions, it's quite straightforward. So the main algorithm people use in this domain is something called sequential quadratic programming, or SQP. The basic idea of sequential quadratic programming is as follows. You kind of take the minimal Taylor series you need to make your optimization problem with constraints interesting. Do you see that? So in particular, we are going to take a second order Taylor series for the objective and a first order Taylor series for the constraint. And this is the thing we're going to iterate. So this is kind of like, you know, a souped up version of Newton's method. But there's a problem, which is that this inequality constraint we still don't know how to deal with, right? And so it turns out that the kind of standard algorithm for dealing with this kind of stuff is very simple, which is the following. I have some iterate xk, right? And I look at my list of constraints, and I can figure out some of my constraints are probably violated by my current iterate xk, right? If those constraints are violated, I'm going to add them to my list of active constraints. Moreover, if I look at these kind of dot product arguments like what we derived, and I find that I'm pointing, like the gradient moves me into the interior of the feasible set, then I'll remove it from my feasible list, and I'll iterate this thing. So at the beginning of our next lecture, maybe we'll derive this algorithm called sequential quadratic programming, where what we're going to do is maintain a list of active constraints. The active constraints are going to take this inequality sign and convert it to an equality sign. And we're going to find that we can write a closed form solution to that equality constraint problem. This is just least squares again. Spoiler alert. And then that's what we're going to iterate. Okay, so we're out of time today, so we'll start with that next time. But this is all just a very simple application of the KKT conditions we just derived, where we're just turning on and off feasible things by using the KKT conditions to figure out which ones should become inactive. Okay, so with that, everybody have a delightful rest of your Monday. Don't forget your homework, and I will see you on Wednesday.